Hello, today's video we're looking at solving polynomials. However, solving polynomials, that's a very maths A-level topic. So to make it more further maths, let's solve polynomials with complex solutions potentially involved. And this will also be part one of a two-part video. I decided to split it up. Worth mentioning also that this topic is very linked to another topic in further maths A-level called roots of polynomials. There are strong similarities, but the methods we're looking at in this video are a bit different to that topic. This is more about finding the solutions, whereas roots of polynomials is more about the links between the roots and the original equation. Okay, so to kick things off, let's look at something we're super familiar with, which is quadratics. We know this stuff so well by now, and we've already been looking at quadratics in other videos about quadratics and their link to complex numbers. Because if we have a quadratic that only has real coefficients, there are only three options that can happen. We know them all very well. Of course, it can be two distinct real roots, or it can be one repeated root, or we can have two complex roots. Except we can be more specific than that, because those two complex roots can form a conjugate pair. In fact, they'll always form a conjugate pair. How do we know that though? Well, let's look at how we solve quadratics. One way of solving quadratics is to use the quadratic formula. And the only part of the quadratic form that could possibly lead to an imaginary number, which of course would then lead to a complex number, is this part here, the square root. When we square root a negative number, we get an imaginary number. And what do you know? Look in front of the square root, we've got a plus minus, and that is what leads to us always having a conjugate pair if we have complex solutions. Because the real part's always going to stay the same each time, because the minus b over 2a would form the real part, and then the plus or minus, the imaginary part, which is going to be the square root of the discriminant over 2a, is going to be the only difference between the two roots, which is what conjugates are. They're just two complex numbers where the only difference is the plus and the minus in front of the imaginary parts. So yes, we can confirm if a quadratic only has real coefficients, any complex roots must be in a conjugate pair. Now, quadratics are all right, but you know what? Let's ramp it up a notch. Let's look at something a bit cooler. Let's look at cubics. But the thing is, cubics are also something we already know how to solve. The way we used to solve them is we would take a cubic, we'd start off by finding a factor by using the fact theorem, plugging numbers into the equation, finding one that worked. Once we had that, we'd have a factor. So for instance, plugging in x equals 3, in this equation it works, and therefore we know that x minus 3 is a factor. Once we've got a factor, we can then use algebra division to split up the cubic into that linear factor and a quadratic factor. For instance, for this question, that would look like this. And then once we've got a quadratic factor, it's all easy because we then just have to solve that quadratic to get the last two solutions, or roots, if you will. So our quadratic is quite easy. It can be factorized, and therefore our three factors lead to the three roots of x equals 3, or 2, or 1. Okay, now if we're dealing with cubics that might have complex solutions, it's actually a very similar process. We're still going to be starting off with finding a real root and then using the corresponding factor to then split up the cubic into a linear factor and quadratic factor, and then just dealing with the quadratic how we normally would. So, for instance, let's look at what those different scenarios possibly could be. If we have a polynomial of degree 3, remember that's just a posh way of saying a cubic. Degree 3 basically saying the highest power in the polynomial is 3. If this cubic has all real coefficients, then these are the different scenarios we can have. First of all, we find a real root, use the factor to split it up, the cubic, into its linear and quadratic, and then the quadratic has another two distinct real roots, leading to a total of 3 distinct real roots. Example of that would be this cubic here, which we just looked at, 3 distinct real roots there. Another situation we could have is we could have a situation where we find one real root, and then the quadratic we're left with then has repeated roots. That would lead to one real repeated root, if I can say that correctly, one real repeated root that appears twice, along with one other distinct real root. The other way that can appear, of course, is if you find a real root, and then the quadratic you're left with has two distinct real roots, but one of those two roots is one of the ones you already found. An example of that would be a cubic that looks like this, where the repeated factor is x minus 1, leading to the solution of x equals 1, and then, of course, the x leading to x equals 0. Okay, and then another situation would be we find one real root, and then the quadratic we're left with has repeated roots, but those repeated roots are the same as the real root we'd already found, leading to only one real repeated root, except it's been repeated a total of 3 times. Example, that would be something that looks like this. You might recognize this cubic by its binomial expansion coefficients there. Another situation would be we find one real root, we're then left with a quadratic, we solve the quadratic, and it has two complex conjugate roots. So therefore, that would be one real root and a conjugate pair of complex roots. An example of that would be this cubic, I should say, yeah, with solutions x equals 0, x equals 2 minus I, and 2 plus I. Right then, is that it? I know what you're thinking. You're thinking, can all 3 roots be complex? Is that possible? Well, I've got a simple answer to that, and the answer is no. No, it's not possible. If the cubic only has real coefficients, we cannot have all 3 roots being complex. And the reason for that, I'm not going to go into it from an algebraic perspective too much. Let's just think more about the graphs, and that will sort of hopefully explain why this has got to be. Because no matter how we draw a cubic graph, it's always got to cross the x-axis at least once, no matter what way I draw it. Whether that's a positive cubic shape, whether it's a negative cubic shape, whether it's a cubic that has 2 stationary points, whether it's a cubic that has 1, or even no stationary points. However I draw it, they're always going to end up having parts below the x-axis and parts above the x-axis. So that means we can confirm that a cubic will always have at least one real root, and therefore that means those 4 situations we looked at before are the only possible solutions or ways of having solutions for a cubic with all real coefficients. Okay, let's look at an example. Okay then, so here is our example. We've got a cubic equation, and we're given that one of the roots to the equation is 1 minus 3i. We've got to, for part A, find all the 3 roots for the equation, and then part B, effectively factorize the cubic. Now, if this question was just part A, then there are other methods you could do to solve this question, alternatively to the one I'm going to show you here. However, because of the part B that's also there, the method I'm going to be doing is probably best for this particular question. Okay, now we're given one of the roots, and if we're going to approach this in a maths A-level sort of method way, we would probably go, well, if 1 minus 3i is a root, then therefore we know this is a factor of the cubic. And therefore your natural reaction might be to say, okay, I know what, I'm going to take the cubic, use algebraic division to divide the cubic by this factor. However, you should avoid doing that. In fact, in maths A-level, further maths A-level, I should say, if you're ever in a scenario where you think you're going to need to use algebraic division with a complex factor, a factor which has some sort of complex number in it, then you shouldn't be, basically. There are ways in further maths A-level to avoid having to ever do this, because it's possible, but it's just a bit more of a pain than it is worth. So, if you're in this sort of scenario, it means you're missing a much simpler idea or trick. In the case of this question, well, we've got a cubic with all real coefficients, and we've got a complex solution. And if we refer to the 4 different scenarios we said had to be true when solving a cubic, we said earlier that if we have complex solutions to a cubic with all real coefficients, we said complex solutions have to be in a conjugate pair. Therefore, instantly, without doing any working, I know that z equals 1 plus 3i must be one of the other roots to the equation, because 1 plus 3i is the conjugate to 1 minus 3i. Okay, therefore it means I know that z minus 1 plus 3i is a root of this equation, or sorry, a factor of this equation as well. What I'm going to do is use this to my advantage though, because I know from solving quadratics that if I multiply these two factors together, I'll get a quadratic with only real coefficients. And that's going to be a lot nicer to deal with. So you could just multiply these brackets, or later on after you've done the roots of polynomials topic, you will be probably, got used to dealing with tricks to make this sort of idea quicker. You'll realize you can use the sums of the roots and products of the roots to help speed the process up. But basically, those two factors will multiply out to get the quadratic z squared minus 2z plus 10. Okay, now what we can do is we can use algebraic division now, and that's because we've now got something which has got all real coefficients, so now it's actually quite easy to do. So that's exactly what I'm going to do. We're going to use algebraic division. I'm going to use long division here, but whatever method you like using that can help you with this sort of question, that's absolutely fine. So writing it out, z cubed plus 2z squared plus 2z plus 40. There you go. Okay, so z squared times by something equals z cubed. That would be z. Multiply the quadratic by z gets us this. We then take them away. Z cubes cancel out. We're going to end up with 4z squared. And we're going to end up with minus 8z. And then we're going to end up with plus 40. And then the last bit is quite easy. We can see it's going to be plus 4 there, multiplied. Z squared times by 4 equals 4z squared, which is what we want. So therefore, multiplying 4 by the quadratic gets us, unsurprisingly, exactly what we just had, which takes away to make 0, which is good because it means that indeed the factors we have found are actually factors, but more importantly, it tells us the last factor is z plus 4. And therefore, we know the last solution is just, of course, z equals minus 4. So the 3 roots, have to write them all out at the end to make it obvious, all in one place. Very easy on these sort of questions to go, oh, I've done. You sort of are, but it's good to give a sort of final conclusion, final answers clear. So those are our 3 roots to our particular equation. As I said, there are other ways of if you're just trying to find the roots, there are other ways of going about that, but I approached in this particular way because, what do you know? We've actually already done part B at the same time as doing part A, because it means we know this particular cubic factorizes to be, we write part B there, part A there. We know the answer is z plus 4 times by the quadratic z squared minus 2z plus 10. I know I had to write it in this way because we're told that A, B, and C are real constants. So it's not as if I could have chosen another 2 different factors of the 3 factors to form my quadratic, because A, B, and C all had to be real. And if I had one of the complex factors here, it just wouldn't be like that. Okay, there you go. That's the approach to these questions. Not really anything new, except for using this idea of complex conjugates being the only option if you've got complex solutions to a polynomial with real coefficients. Okay, thank you. Goodbye.